Here, we'll take a look at section 2.1 at the first three learning objectives that we have there at the beginning of the sheet. You'll always have learning objectives on the top of your note sheets. So we'll look at the first three here in this short video. To get started, we need to understand the definition of a relation, which is just basically any set of ordered pairs. First components are your x values, second components are the y values, but we do need to be familiar with these two terms. Domain is the word we use for x values, and range is the term we'll use for y values. So to get started, we'll just very quickly set up the domain and range for these two, for this relation, noting that the domain is just a listing of the x values and the range is the listing of the y values. So that's simple enough. Now let's take this one step further. Let's determine if relations represent a function, if we can classify them further as something we call a function. So let's check out the definition of a function. It's a special type of relation where there is a correspondence between your x's and your y's, but the correspondence is such that each element in the domain corresponds to exactly one element in the range. That's what separates a relation from just being a relation or being a function. So let's see if we can classify these three relations as being a function or not based on that definition. What we're looking for is one x corresponding to exactly one y value. And if we look here in this first relation, each x, 2, the x only 2 there, corresponds to one value, -3. X value of 5 corresponds to one value, 7. X value of -4 corresponds to one value of 8, and so on. So yeah, the x's correspond to exactly one y. Look at the next one. It's a bit different though, because if you notice, the x values are repeated. That tells me the value of 2 is corresponding to more than one y value, in this case, 2 distinct y values. That gives us a problem. It's a relation, sure, but it's not satisfying our condition for a function. So if those x values repeat, it's not a function. Finally, the last one, if we investigate these ordered pairs, each x corresponds to exactly one y. The x values are not repeating themselves, so sure, it's a function. Sometimes these relationships can be set up as mappings, as you'll see below. We can take these and list out the x's and the y's and just show with a series of arrows what the relationships look like. So it might be better if you're a visual learner to see it this way. So let me go ahead and set up these relationships. So for the first relation, we have a 2, 5, -4, 3. And then the y values are such, and just the mapping shows one x going to one y. Clearly, that's a function. When we set up the next one, there's actually only 2 distinct x values, 4 distinct y values, and when we set up the mapping, we see that the 2 corresponds to 2 different y values, and the -4 corresponds to 2 different y values. That's why this one was not a function. And then finally we could set that one up with the 2, 5, -4, 3 corresponding to all of those to a single value, but notice each x corresponds to exactly one y, so we're still within the definition of a function. Finally, we'll look at if an equation, or basically an equation that's a relation, does it represent a function? So let's take a look at these. To determine if an equation represents a function, we're going to take these equations and solve them for y and then investigate what happens. So let's take the first one. Very simply, we can solve it for y by taking the x squared over. So it solves for y equal 4 minus x squared. We're done. And if we put in some x values, each x will correspond to one and only one y. Oh, let's solve this one for y. Let's take over the 2x. So we'll get 16 minus 2x and then divide by -4. We'll have y equal -4 plus 1/2 x. That one solves pretty easy for y. And if we put in an x value, we'll get one and only one y value out of that. That's what we're looking for, if it's a function or not. So yeah, this one's a function. Nothing funny happening. This one's a function. Let's solve this one for y. Let's take the x squared over. This one's a little different though, because to finish this up, to get rid of the square on the y, we've got to square root each side. And when we square root both sides, we've got to remember to incorporate a plus or minus, which gives us our equation to be y equal to plus or minus the square root of 4 minus x squared. Here we have a problem. This says for every x that I put in, I'm going to get 2 y values, which, as we saw before in the middle mapping up here, that violates the definition of a function, so this one is not a function. Plus or minus causes a problem. Causes us to get 2 values of y for each value of x. And finally, let's solve this one down here. I can't add the 3 first because it's there underneath the radical, so to dig that thing out, we're going to have to get rid of the radical by squaring both sides. Doing that causes the radical to cancel. We get 25x squared. Now we're squaring both sides. We don't need plus or minus. We only need plus or minus when we square root both sides. And then that'll be 25x squared plus 3. If you put in 1x and work it out, you'll only get 1y, which means it's a function. So what would be the moral of the story here? All of these were functions except for the middle one that ended up with a plus or minus. So what observation could I make here? If there's a plus or minus, it's not going to be a function, but where did the plus or minus come from? Came from the square root. And why did we have to square root? Because there was a y square. So if there's a y, if a y square appears in the equation, I'm not doing a really good job of writing, am I? Our conclusion is it's not a function.